So first, do you have any particular questions that you want me to look at or go over? Yeah, Mika? Yeah, so a question on the coefficient. The place where that's probably going to come up is, when we're looking at the work energy theorem. Let's see if I can find a good one. Do you have one in mind? Number 3 on exam 3 of which semester? Oh, like this one right here? Okay. Let me, I'm going to erase this and we'll talk through it. I think we did this one for the quiz when we were getting ready for the quiz. This will be like your free response. So you will have 8 free response and they'll be broken into 4 different questions where you have 2 per question. So 4 free response questions each with 2 parts. So here I have a block with a mass of 10 kilograms. Oh, I'm sorry. No, this isn't like your free response, but you could have one like this on your on the multiple choice part. All right. So I have a block that's sliding and has a certain velocity with a speed of 2 meters per second. So v is 2 meters per second. That means over here, it has kinetic energy. But then it comes over here and it has a speed of 0, and so all of that kinetic energy has been lost. All of that kinetic energy has been put into the work that has been consumed, if you will, by friction. So that kinetic energy then is equal to the work that is done by friction. That's sort of your beginning point. I mean, all of these questions in the first chapter 5 are going to have something to do with conservation of energy. And in this case, we're looking at how all of this energy goes into the work done by friction. So I say 1/2 m times v squared is equal to the work done by friction. That's going to be F times D. And then we need to remember, how do we find the frictional force? And that is that the frictional force is equal to mu times the normal force. You have the equation sheet. It's in your workbook. It's on the website. This is not on that equation sheet, but you might need to know this for the exam. Likewise, you'll need to know, F equals ma. You need that for finding weight of objects and how to find the normal force. So you sort of need to keep those things on the tip of your fingers. Or not on the tip of your fingers, in your mind. Okay? I don't know if you could fit that on the tips of your fingers. Anyway, F is equal to mu times the normal force. That's going to be mu. In this case, because it's a horizontal surface, it's mu times mg. So I can take this and put it right here for FD. And so I get 1/2 mv squared equals mu mg times d. And now I'm looking for the coefficient. I can cancel out those m's. That is, I just, divide through by m, and I solve this for mu. So to solve it for mu, it's going to be 1/2 v squared divided by g times d. That's 1/2 of 2 meters per second squared divided by 10 meters per second squared times d, which is, it travels 2 meters. So that's 2, it's 1/10, so it's 0.1 is the answer. I know that's kind of it seems like a complicated problem, and it's probably one of the more difficult problems on this exam, but the idea is still pretty simple, that my kinetic energy is all consumed by work. That is the work done by friction. Where it gets difficult is remembering how to do the kinetic friction and apply our normal force and then figuring out what is the speed. Yeah, Chloe?
This is kind of similar to that one, but could we do number 2 on the previous page as well?
Sure. And then I saw your hands. Did y'all have a question about this one?
Yeah.
Okay, we'll come back to that, Chloe.
I watched it and it was 0.3.
Yeah.
Oh, did I do it wrong?
Kinetic energy minus the work done by friction equals kinetic energy for that one.
Yeah.
Oh, yeah. I'm sorry. I worked this like it was coming to rest. but in reality, it's actually coming to a speed of 2 meters per second. Remember, you got to read these questions. Don't assume that you know what they say. That's what I did, right? I assumed that it was coming to rest when in fact it's not. So let me erase some of this stuff over here. So this is not wrong. It's just taking wrong assumptions. But I did it correctly. But the correct way would be to say that the kinetic energy minus the work done by friction is equal to the final kinetic energy. The initial kinetic energy, that's 1/2 of m times 2 meters. No, 4 meters per second squared, excuse me. Minus the force times the distance is equal to 1/2 m times 2 meters per second squared. Okay? You'll see what Mika, you asked that question. You see what I did there? Let me show you my mistake first. It's probably not clear unless you've seen this problem recently. So here, I was working a different problem where I said, this object comes to rest in 2 meters. It starts at 2 meters per second and it comes to rest in 2 meters. What is the coefficient of friction? In which case, I say that kinetic energy is the work done by friction. 1/2 mv squared is F times d, and then I solve for mu. But I hadn't really read the problem. I just thought I knew what it said. But really, I start with some kinetic energy, which is 1/2 m times 4 meters per second squared, which is the initial speed, minus the work done by friction is equal to 1/2 m times the final speed, which is 2 meters per second. Then I do the same stuff that I did over here, but solving for mu. And then find that the mu is equal to 0.3. Is that what you said? 0.3. Okay? 0.3. Sorry if that confused you, but it's actually probably good to see those different types of problems, because that's a good way that I could change that problem up, for example. Like you'll probably see something similar to that, but it'll be different, probably in that way. There are various ways to ask that question.
What would it say if it was your way?
If it was my way, it would say the block starts at 2 meters per second, and it comes to rest in 2 meters. After traveling 2 meters, it stops. In which case, all of that 1/2 m times 2 meters per second squared, that kinetic energy, is consumed by the frictional force. Okay? All right. What was that? Oh, on the previous page, right?
It's the one with the block,
The what?
the wedge in the block.
Where is it?
It was just on the page before.
Exam 3, fall 2019?
No. If we were on exam 3, fall 2021,
Okay.
just the page before that. Yes. Bye.
Okay, so this is your free response, something really, really similar to this. It's going to have similar figure with a block. There will be some kinetic frictional force. I will not require you to calculate the normal force, wherein, to find the normal force, if you had the weight, you would have to say the force weight times the sine of 90 minus theta. Not going to make you do that. We're not going to have to do any 2D forces with inclined planes. This problem is actually much simpler to this. The first part, it asks what energy is lost due to friction. Well, the energy that's lost due to friction is the work done by friction, and that's F times D. This distance right here is the distance over which the frictional force acts. That's my distance D. But notice this is a 3, 4, 5 triangle. You'll probably have a similar triangle. I know you know Pythagorean theorem. So this is equal to 5. But if you forget, goodness bless you, 3 squared plus 4 squared, square root of that is equal to 5. It's a special triangle, 3, 4, 5. The frictional force is 5 newtons. The distance now is 5 meters, so it's 25 joules for that first one. And then the second part is what is the speed at the bottom of the inclined plane. So if there was no friction, we would say that the kinetic energy at the top is equal to the potential. We would say that the potential energy at the top is equal to the kinetic energy at the bottom. Okay, but there is friction. Along the way, there's a work done by friction that consumes this 25 joules of energy. So we'll say mgh minus the 25 joules, or you could say mu mg if you want. That would be the frictional force. So is equal to 1/2 mv squared. Okay, so I know the mass here. I can put it in. Actually, I'm going to work this a slightly different way. I'm going to say that mgh minus the frictional. Oh, actually, no, never mind. I'm not going to do it that way. That would be too complicated. We'll just do it this way. Say mgh minus the 25 joules is equal to 1/2 mv squared, and I solve that for v. So v is going to be m, which was 10 kilograms, times 10 meters per second squared, times h, which is 3 meters. So this is the other relevant distance, the height of that object, minus the 25 joules. That's the work done by friction. And then I have to divide that whole thing by 1/2 m, half of 10 kilograms, and then take the square root of that whole thing to find the answer. So that's 100, 300, 275 divided by 5. What's that? The square root of, you might know the answer. 7.4. Okay. You're probably very similar for the free response. I think it's number 3 if I'm not mistaken. No, it would be number 2 on your exam. Okay. Again, your free response will look a lot like this, except it's also going to have that tension in the string or Ferris wheel problem where it's calculating either the normal force or the tension in the string. Right. Other particular questions? I think somebody else had a question. Is that right, Tara?
Can you do number 9 from the fall 2020 exam?
Sure.
I mean, number 19.
Number 19. I think that's this one, right?
Yes.
Yeah. Sure, I got this going. Yeah. So a person has a mass of 90 kilograms and is sliding forward on a frictionless track at 2 meters per second. The person catches a medicine ball traveling in the opposite direction of the motion with a speed of 8 meters per second. What is the person's new speed? Remember I said it's helpful to draw pictures? You really want to draw pictures with these because you have to be careful with the signs of the velocities. If you get the signs incorrect, then you're going to get the problem wrong. And you're going to think you got it right because I did that too for you, right, to figure out what is that wrong answer. So really draw a picture. Here's my person. They're traveling in this direction at plus 2 meters per second, and they have a mass of 90 kilograms. And then there's a medicine ball where somebody has thrown toward them with a mass of 10 kilograms, traveling at a speed of 8 meters per second. Boy, they can throw that thing, 8 meters per second. Anyway, now these two are going to collide, and they will come together and move off at the same speed. So I have now the medicine ball and the person, and I want to know what direction are they going to go, or rather, what is their speed? I can look at this and know that this whole thing is going to keep going in this direction because the person has 180 kilogram meters per second. That's their momentum. And the ball has just 80 kilogram meters per second. So my net momentum is to the right. So I'm going to go ahead and draw my arrow just because I know that the velocity is going to be positive from looking at the momentum. And then I say that PI is equal to PF. Anytime I have these collisions where both objects are moving, right? Remember in chapter 6 there are two types of problems. There where you run into an immovable object. That's where we're applying Newton's second law, that F equals delta P over delta T. And then there's these where you have these collisions of particles that bounce off of one another, where we say that the conservation of momentum PI is equal to PF. All right, so I say 90 times 2 plus 10 times negative 8 is negative because it's to the right, is equal to 90 plus 10 times my V final. This is one of our perfectly inelastic collisions because the two objects move off at the same speed. That's 100 equals 100 VF. Our VF is equal to 1 meter per second. And that's the person's new speed.
And there's another type of problem like this that will we ever have to do the ones where like they can bounce off of each
Yeah, yeah. So you're going to have to do that type of problem, probably in the multiple choice and in the free response. You're going to have to do it several times. Okay.
Do you have a
Bryce?
response like number 4 on fall 2019? Do you have any other examples of that? Basically the same as like it's the last thing just kind of like kinematics equations, just for like alpha and omega. Do you have like another example of that free response?
Number is this number?
So for fall 2019, it's like the fourth.
Fall 2019 on the free response.
Yeah, for 4.
I don't see the free response on this. Do I not
Was
have
it, that was it.
You're just
right here?
Yeah, let's finish.
Oh, about.
Never mind.
In 2019, at the very end, the free response is at the very end.
Oh, okay.
Isn't that
What-
the only example we have of that, or is it?
Which one? Number
Yeah, right there.
24?
Is that going to be similar to what we have on this?
Number 24? Oh.
Yeah.
Number 24?
Yes.
Well, no, there are lots of these different. I mean, I think every exam has one of those of various types. So, like number 22 right here, right? That's the same question. Really, not just that question, but this is the same question. This is the same question. All of those use this idea that the initial momentum is equal to the final momentum. So you can find 3, sometimes 4 questions that are conservation of momentum basically on every exam. Y'all like my new ringtone? No. You don't care, do you? Do you care? Okay, Lily?
Number 4, 2019.
This one? The supermarket checkout? Yeah, so, yeah, this is I want to know the work. So this person, here's your can, and they're applying a force of 6 newtons, and they make it move across a distance of 0.5 meters. So work is FD cosine theta. Since the angle, the force, and the displacement are in the same direction, that angle theta is equal to 0. So cosine of 0 is equal to 1. So it's just going to be 6 newtons times 0.5 meters. Our 3 Newton meters are 3 joules. So B is the right answer. And you will have some like that where it's just fairly straightforward, calculating the work, force times distance. You'll also have some where you have to include the angle. Oh, that's more complicated. But where you have to include the angle to find the total work. You want to look at number 12 right quick? Number 12 is similar to that, but it's made a little more complicated because, actually let me read it.
They also have
Oh no.
coefficient.
Yeah, but this one's not complicated, at least this one isn't, because all I'm asking here for is the work done by the man on the block. So I'm only asking for the work done by this force. I'm not asking anything about the friction. All right, so we've talked about this, how different forces will do work, and other forces might not do any work at all. But in this case, this force is doing work. So in order to find that work, it's FD cosine theta. That means that the work is 45 newtons times the distance or the displacement, which is 5 meters, thank you, times the cosine of the angle, which is 28 degrees. And then if I do that, I get 45 times 5 cosine of 28. which is 200 joules. Okay, so this force does 200 joules of work. Now, let's go ahead and determine what is the work done by the frictional force, because there is a work that's done by the frictional force. That frictional force is mu times the normal force. That's going to be 0.1 times 80 newtons. Oh, wait, no, it's not that easy, is it? Do we ask this? No.
Isn't it? Why would the normal force just comes from the surface of the block, doesn't it?
The normal force is actually less than 80 newtons. Why is the normal force less than 80 newtons? Why, Lincoln? He's pulling up on it. You're not going to see a problem like that, so you're welcome. You're welcome. You're welcome.
So what was the answer on the, because that was on the quiz.
Yeah, that was on the quiz.
What was the actual answer?
For which one?
Well,
The answer is 200.
what about the friction?
You don't worry about the friction, because it's not asking what is the total work done on the block. It's asking what is the work done by the man on the block. Not the total work, in which case you would have to consider the friction. And it gets to be a fairly complicated question because you have to figure out what is the normal force in order to do that. And the normal force is going to be equal to the weight minus the y component of that 45 Newton force, right? We did a question like that back in chapter 4, where if I'm pulling up on the block, then the normal force is actually less than the weight. But in this case, it's not a complicated problem. It's just what is the work done by the man on the block, which would be 45 times 5 times cosine of 28. Okay? So 200 joules is the answer. Let's not worry about this right now. It's not important. Yeah, Bryce?
I actually meant number 22.
Okay, that's a good question too, though. Number 22.
If
Yeah.
there was any more examples of that. Like number 22 in the free response.
Oh, in the free response.
It was number 2 or something. It was with the flywheel.
Oh, that's chapter 8. What exam is it? Fall 2019.
Because like asking for the normal force and such acceleration as well.
This one right here?
Or actually, yeah, for each chapter.
Oh no, this isn't chapter 8. This is a kinematics question. You want to do number 22?
Yeah, that's chapter 7, isn't it?
Yeah, this is chapter 7.
It
Yeah.
was the only example that I had seen out of all the examples.
Yeah, you're not going to have a kinematics question on your free response, but you'll certainly have it in the multiple choice. Okay? And the free response aren't meant to be more difficult. I don't think that they are more difficult. They're just questions that I think are important that I want you to get. And that's why I tell you what they are so you can sort of prepare for it. I really want to see you do perfectly on those questions. That's why I tell you what they are beforehand so that you can practice them. But anyway, I don't mean them to be more difficult. I consider them a similar difficulty to the multiple choice. All right, so flywheel on an engine is at rest. That tells us something about this problem. It tells us that omega naught is equal to 0. I'm going to go ahead and do all my units in revolutions per second because I see that everything else is in revolutions per second. Then it accelerates at 4 revolutions per second squared. And I ask how many revolutions, that is, what is theta equal to for it to reach a final angular speed of 12 revolutions per second. So what I've done there is I've just written down everything that I know. I'll have my equation sheet nearby, but I'm going to write those two equations down. Omega equals omega naught plus alpha t, and theta equals omega naught t plus 1/2 alpha t squared. I started to keep those on the side. I said, you'll have your equation sheet. It'll be on the front of your bubble form in that little box with just 5, 6, and 7 equations. So I'm looking for theta. I know to find theta, I have to do this. I know omega naught. I don't know t, but I know alpha. So I don't know either theta or t. So that means I'm going to have to figure out what is the time for it to reach this. But look, I know omega naught, and I know alpha. I know the time, so I can figure out the time for it to get up to 12 revolutions per second, and then I can determine what is the angular displacement in that time. So the first part is just to say omega equals omega naught plus alpha t. Omega is 12 revolutions per second equals 0, I'll just leave that off, plus 4 revolutions per second squared times t. And I solve that for t. T, of course, is 12 divided by 4, 3 seconds, which, by the way, was the answer for part B. So I listed them out of order so you could think about, well, what is it that I know and what do I need to know? And then I want to find out what is theta. So that's omega naught t plus 1/2 alpha t squared. Omega naught is 0, so that term just goes away. And so I get 1/2 of alpha, 4 revolutions per second squared, times 3 seconds squared. That's 18 revolutions. Whenever you're using your kinematics equations, it doesn't matter if you change the units or not. What you should look at when you're doing these kinematics problems is look at the options. Are they in SI units? Are they in revolutions or degrees? And whatever those answers are, then you should just match them. You'll be able to tell. I don't think that I had any where I have the units in the problem are different from the units in the answers for kinematics. I think I have done that in the past, but not for y'all. And then, but if you're doing centripetal force, or if you're doing the translating your angular to your linear quantities, the S equals R theta, V equals R omega, A equals R alpha, those things, you must be in SI units. It's only in the kinematics equations. Because you see here that my units are all going to work out, right? That I had revolutions per second squared, they cancel there with those seconds squared and gives me revolutions, not revolutions per second, just revolutions. So do your dimensional analysis to make sure your units work out. But if you're doing centripetal forces or translating those linear and angular quantities, you must be in SI units. You're never going to go wrong in SI units. It might just make a little extra work. So if you ever have any doubt, just convert to SI units. Okay? All right. Yeah.
Just real quick, I'm assuming, so in terms of power, do we just really need to know what that is?
Yeah, you just need to know what power is. I didn't ask you to calculate it on the test. I mean, it doesn't usually make it onto the test. We're going to see power again next semester, but I might ask you what the units are. Power, I'm not saying this is on the exam, but the units are a watt, and that's equivalent to 1 joule per second, and that's equivalent to, what are the basic SI units of that? Kilogram meter squared per seconds cubed. I think I did that right. So it would be 1/2 mv squared. That's energy. Yeah, so that's kilogram meter squared per second squared. But then you have to add another second. So yes, per seconds cubed. Y'all see what I just did there? Define those basic SI units. The SI units for energy are 1/2 mv squared. And so m is kilograms, v squared is meter squared per second squared. And then I know that power is energy over time. And so that's where that seconds came from, that 1 over seconds, to give me the basic SI units for power, which is kilogram meter squared per second cubed. That's how if I ask you what are the basic SI units for energy or work or power, that's what you do. I'm pretty sure there is a question like that. Oh no, that was on your quiz where I asked you that, right?
There was a question like that.
Yeah, so I might be conflating those two. I don't know if it's on the exam or not. Okay. What else, y'all? These are all good. These are all on the exam for Wednesday, okay? Yeah, Donald? Okay, 2021, question 8. Where am I here? Okay. Is it this question, number 8? Is that fall 20? Yeah. Is it? I'm going to erase what I have here so we can talk about it. I'm not distracted. I've done this in the help session before. Y'all I sent out a message earlier about a seminar tomorrow. I meant to announce it in class today, but I just forgot. But if you come to that seminar, it is extra points, so you get 5 points extra credit. But it's also just going to be a really great opportunity to talk about graduate school, which I know a lot of y'all are like pre-professional, just like a brain, or pre-professional, pre-med, pre-PT, pre-OT, whatever it is that you are. But graduate school is a great option for folks if you want to go to graduate school. This guy that's coming is going to talk about LSU chemistry, but even if you're biology or whatever, that it'll apply there as well. Graduate school is a good option. About a third of our chem majors will take that option. And usually there are jobs around here for PhD chemists. They're pretty high paying jobs. They usually start around a couple 100,000 or so. PhD chemists will make as much as a medical doctor, frankly, after they've been in a lab for a while. But you don't pay anything for graduate school. That's kind of one of the nice things. And it's a different kind of work. It's a less high stress work. So anyway, come hear what he has to say. Number 8, right? That's it, Donald? Yeah. So here, I want to know the total work done on the block. So this one's different from the question before where it was asking what is the work done by the force, by the man on the block, because there I was just asking for the work done by that individual force. But here it's asking for the total work done on the block. Now notice I have this one force right here. It does work. The work done by it is equal to FD cosine theta. That's 8 newtons times 3 meters times the cosine of 60. And then I have the work done by this force. That's the work done by capital F. The work done by little f is going to be equal to 1 newton times 3 meters times the cosine of 180. All right, so that's going to give me a negative 3 joules. This is going to give me a positive 12 joules. And so 12 minus 3 is equal to 9 joules. Okay? So there are 2 forces there that are doing work. There are other forces as well acting on this block. Like there is the weight of the block, but that doesn't do any work at all because it's perpendicular to the displacement. And likewise, there is a normal force, but that doesn't do any work at all either because it's also, perpendicular to the displacement. The only 2 forces that do work are this frictional force and the x component of this 8 Newton force, which is 8 newtons times cosine of 60. That is that x component. You will have a question like that, Donald. You will have one similar to that, so make sure that you're prepared. But you find the work done by each individual force and then add them together. But recognizing that little force F does negative work because it's opposite the direction of the displacement. Okay?
Number 9.
Hold on. Braden, I think, had asked, he had his hand up. Did I answer your question? You sure? Okay. And I think Lily also had the next question. So I think you've exceeded your number of questions. Lily?
I just wanted to do some form of centrifugal motion.
Yeah, okay. And we will come back to it. What was the question?
No, it was a theoretical question. I'm just bad at those.
Let's look at some centripetal motion questions. We haven't done that many of those, have we? Sometimes these are in chapter...
Aren't these just chapter 7?
Yeah, but sometimes they're on exam 4, so just beware. Isn't that right? Yeah. Yeah, like all these are they're on exam 4. All right, let's look at number 14. This is what exam is this? Fall 19, number 14. This is going to be like the one on your free response, either like this or like the ball and the string. They work similarly. So here I have a Ferris wheel. I'm just going to draw the top half of it since we're looking at the highest point. And then I have a chair up here, and then there's somebody sitting in it. And I want to know what is the normal force. Now, this person has a weight of 100 kilograms. That means if it wasn't moving, that the normal force would equal to 1,000 newtons. But I know at the top of the trajectory, is he going to feel lighter or heavier at the top of the Ferris wheel? lighter, right? Like you go over hills in your car. I mean, we don't have hills around here, but back in Mississippi, we had hills, and you go over hills and you come up over a big hill, and it feels like you're coming up out of your seat if you're going too fast. So that's because the normal force gets smaller. That means I can get rid of all of these. It's either A or B. It has to be either A or B. I'm betting that it might be D, but I'm not certain about it. So I know that it has to be less than 1,000. So I can draw my forces. I have one force that's down, that's my weight, and I have another force that's up, that's my normal force. Sum of the forces is going to be Fn minus Fw, and that's equal to m times AC. And AC, that's my centripetal acceleration. Notice that it's negative. So I'm going to go ahead and put a negative right here. Kind of like how we did with the elevator problems that we had back in chapter 4. If it's going up, accelerating upward, or accelerating downward, then that would change the normal force or the tension in the rope. Identical problem, exactly the same, except now I'm rotating. To find my normal force then, it's going to be Fw minus MAC. That's going to be the weight of the guy, which is 1,000 kilograms, or 1,000 newtons, excuse me, minus the mass of the guy, which is 100 kilograms, times the centripetal acceleration. Now, over here, now in your free response, I'll probably have a separate question that asks, what's the centripetal acceleration of this dude? And so my centripetal acceleration is either v squared over r, but I don't give you v, I give you omega. So I'm going to say omega squared r. That's 0.2 radians per second squared times r, which was 30 meters. So that's 0.2 30. I get 1.2 radians, or excuse me, meters per second squared. So that is my my acceleration, and that's what's going to go in right over here, 1.2 meters per second squared, and so that's 100 minus 1,000 minus 120 is going to be 880. Okay? That's like your free response. I might ask you to draw the force vectors. I might ask you to calculate the centripetal acceleration. I'll definitely ask you to calculate the normal force or the tension, depending on what type of problem is it. Is it a Ferris wheel type problem or a ball on a string? Let's look at some others, though, because you'll have some in your free response as well, or in your multiple choice. By the way, just FYI, looking forward, if you look back at some more recent exams in the past 2 or 3 years, you'll see that sometimes we stop at chapter 8. That's not going to happen for y'all. Like, we're going to go on to chapter 9 and maybe even chapter 10. It's not that we've been moving at a faster pace. It's just, there was no hurricane this year. There was no COVID this year. There didn't face the hurdles that we've had in years past. So that means that you get your full money's worth for Physics 101. That was a good deal for y'all, right? So it is a good deal because you don't want to miss these topics, especially pre-meds. Like, you're going to see this, on the MCAT, and chapter 9 and 10 are easy. You saw that in chemistry. Somebody asked me a question. Y'all can ask, how does v squared over r also equal omega squared times r? Good question, actually. So the centripetal acceleration is equal to v squared over r. But remember that v is equal to omega r. So I can substitute this in for v squared. And so I get omega r squared over r, which is equal to omega squared times r. Now, if I give you omega, you can always convert it back to v or calculate the linear velocity and get this value that you need to calculate the centripetal acceleration. But it's easier just to use this other equation and to think about how AC, the centripetal acceleration, compares or relates to the angular angular velocity omega. Okay? Good question. Looking for some more centripetal force problems. Okay, here we go. This is a car that goes around a curve. I have a car that goes around a curve. There is a centripetal force that acts on this car to make it move into that circular path. This is fall 17. So it's useful for y'all to go back a few years as you're preparing. There is a centripetal force. That centripetal force acts radially towards the center of the circle, and it's equal to mv squared over r. I have all these values, so it's a simple sort of plugging in the right values. I have a mass of 1,500 kilograms. That's the mass of your car. The speed of your car is 15 meters per second. That's squared. And then the radius of our curve is 200 meters. So that gives me 1,500 times 15 squared divided by 200. I get 1,690 newtons. FYI, there are other problems where I ask you something about the frictional force. This centripetal force is entirely provided by the friction. So that centripetal force is the frictional force between the road and the tire. So it's a static frictional force because, you know, we talked about this. As our tires rotate, the surface of the tire and the surface of the road are stationary with respect to one another. It's only when you slam on your brakes and they lock up that you start skidding across the road. Remember that, chapter 4? Yeah. So our centripetal force is equal to our static frictional force. So that way our 1,690 newtons would be equal to mu times the normal force. In this case, our normal force is equal to the weight of the car. That would be 15,000 newtons. I just multiplied the mass times 10 to get that weight. And so I could calculate what is mu is going to be 1,690 divided by 15,000 newtons. That's the centripetal force divided by the normal force. And I didn't ask that in this question, but I have asked it in other questions. And that's equal to 0.11 is my coefficient of static friction between the roads and the tire. So I would expect stuff like that on your exam come Wednesday. Okay? Other questions, y'all? Particular questions? Yeah, number 8 on fall 19. And then Tara, we'll come back to you, okay? 8 on fall 19. This one, the spring-loaded gun? Yeah, so let me erase this. We did this, like I said, for the quiz, but let's look at it again because you're going to see it. You will see 2 or 3 spring problems. You see everything, okay? I'm not telling you anything you don't know, but you will see everything. And they're all a little bit different. But in this one, let's see. I shoot the ball straight up. So, again, draw a picture really helps. This ball goes up, and I want to know what is the compression of the spring in the gun. At the bottom, he only has elastic potential energy. At the top, he only has gravitational potential energy. All of this energy goes into gravitational potential energy. So that's 1/2 kx squared equals mgh. And I want to know what is x. So I'm solving this for x. That's going to be 2mgh divided by k. You can just put in the numbers if you prefer, but that's going to be the square root of 2 times the mass, which is 0.02 kilograms, times g, which is 10, times h, which is 5, divided by k, which is 250. Did that all right? Yeah. And then solve that, and I get Only 100. Yeah. I get 0.09. Yeah, 0.089 meters, which is 8.9 centimeters. There are various iterations of this or different versions of it. The other type of version that you usually see is where you have it compressed, and so it only has elastic potential energy, and then you shoot the ball kind of like we did in lab, so it only has kinetic energy, in which case you would say 1/2 kx squared equals 1/2 mv squared. That all of that elastic potential energy is going now into kinetic energy. But definitely you're going to see a couple of questions at least, probably 3, that have to do with springs. Don't forget also Hooke's law, F is equal to negative kx, that the force of the spring is proportional to the compression of the spring. You're just multiplying it times the spring constant. Okay? Don't neglect those. That's a letter grade. 3 questions is a letter grade, so don't neglect them. All right. And Tara, you had a question? What was it?
Would I have any questions for test that's similar to number 18 and 19?
Number on this same exam?
Yeah.
Oh, no. 18 and these 2 right here? Right? No, that's torques. I know that we've been doing it in class. We could have it on the exam, I guess, but we're going to save it for the next one, okay? All right. Number 16? Yeah, you can see something like 16. Let's go through this. This is like, the string in a vertical circle. The tension is least in the top of the circle. True, right? Like the elevator that's going down, the tension is least in the top of the circle. And the tension is greatest at the top of the circle. Not true. The tension is actually greatest at the bottom of the circle. The acceleration is equal to the acceleration due to gravity at the bottom of the circle. That's not true either, that the acceleration also includes your centripetal acceleration at the bottom, and the energy of the yo-yo is greatest at the top of the trajectory. That is true. Yeah, that's true, because it has kinetic energy and it also has the potential energy at the top. Since it's traveling at a constant speed, the kinetic energy is always the same, but at the top it also has that potential energy. Yeah, Chloe?
So is number 1 true because your centripetal force is pulling towards his hand?
Yeah, so number 1 is true because we have tension going in this direction and the weight is going in this direction, and my acceleration is in this direction. So the sum of the forces, Ft plus Fw equals MAC. And so this is negative, these are both negative, and so I can solve, I did this in class, I remember, so I can solve this for Ft, and I find that if I compare it to the tension at the bottom, that it's bigger. It's like Fw, what is it? It's bigger. It's less. That the tension is less. That I have that negative term, whereas in the bottom I have a positive term. Like the elevator problems, right, in chapter 4. Going up, the tension is big. Going down, the tension is small. Okay? I think we're at the end of our time. A few of you walked in, so make sure I get you before you leave. Don't leave the room yet.